Hey, welcome back. So this is part 2 of our series on refraction and Snell's law, and we're going to be looking at the equations and do an example problem or two related to Snell's law. And that's the law that describes how refraction works. So I want to start with this image here though, because I just think this kind of thing is very beautiful. I love to see how light plays on the surface of water. There's a lot of physics and beauty there, all wrapped up together. And those fish, if you were somehow hunting for those fish, or just fishing, I guess you could say, they are actually lower than they appear. They appear to be very close to the surface, but that is because of the effects of refraction. So we're going to be talking about that today in a little more mathematical detail. So let's get to it. All right, so first of all, there is a definition here, a mathematical definition, or you could say a very simple equation, however you want to look at it, called the index of refraction. And so the index of refraction is just a unitless number. You could say, well, why is it a unitless number? And the reason is because it's a ratio of the speed of light over the wave speed, the speed of the wave in the medium that we're talking about. So for instance, the index of refraction for air is 1.00. And what does that mean? Well, that means the speed of light in air is basically the same as the speed of light in a vacuum, because you have this 3.00 times 10 to the 8th divided by 3.00 times 10 to the 8th down here. And so it's a 1-to-1 relationship. So that just reduces to 1.0. And so let's try a slightly more difficult problem. And it says, what is the speed of light in a diamond with an index of refraction of 2.419? So in other words, we have this n value. We know what the speed of light in a vacuum is. Let's go ahead and solve for our wave speed. So how fast light travels inside a diamond, you could say. So we start with this equation down here. I'm not going to have space to rewrite it, but that's what we're using. We go ahead, and since the v value is unknown, like we want to get this v right here by itself, the first step is actually for the algebra for something like this. Like if we have something in the denominator, what we're going to want to do is multiply both sides by that thing in the numerator. And the reason for that is so we can cancel this out and we're left with v in the numerator. And so that's what I've done right here. We're now ready to plug in numbers towards the ends, and we end up with our answer. So that's how fast light is going to travel inside a diamond with a index of refraction of 2.419. Now I will say, notice this is slower than it would travel in space or just regular air. So light does have different speeds depending on what it's traveling through. Alright, and so let's take a look at Snell's law. Snell's law over here is just n1 sine theta 1 is equal to n2 sine theta 2. I'm going to label what these things are. So n1 is the index of refraction for the first medium. So the reason for that is, remember, when we're dealing with refraction, we're talking about light as it goes from one medium to another, and it gets bent as it goes from one medium to another. Then we have two angles here. And there's just a couple terms we're going to want to learn. Angle of incidence, that means the very first angle we're dealing with, and it's going to be measured in reference to the normal. So that's going to be our angle of incidence right here. Our angle of refraction is like the second angle that we can use here, and that's going to be measured from the normal as well. And if you had a cat up here or a guy with a spear or something like that looking at a fish underneath the water, the fish would appear to be, the top of the fish would appear to be over here, whereas really that cat would actually have to aim lower than the fish appears. Alright, and next I want to talk about the fish's perspective. So notice these are important because these are two different things that we're looking at here. In other words, two different scenarios. One scenario is from the cat's perspective. The cat is the observer. The second scenario, the fish is the observer. And they're going to see two different things. So it's important to know what direction the light is traveling and to keep that straight. Like, what's the angle of incidence? What's the angle of refraction? Well, what's the first thing that you're dealing with? Where's that light bouncing off of? In the first case, the light was bouncing off the top back fin of this fish, you could say. And over here, this light is bouncing off the chest of this cat right here. It comes down, it gets bent through the water, and the fish interprets that going back in straight lines, and its brain is telling it that the cat is up here. Now, on further analysis, the fish may know better. The fish may know that the cat is actually lower than it appears, but our brains do make the immediate interpretation for depth perception that light travels in straight lines. That is true almost all of the time, but not 100% of the time. Okay, and so let's take a look at another problem. This one I've created, and it says a light ray of a wavelength of 455 nanometers leaves from a piece of translucent quartz, like this over here, at an angle of 25.5 degrees to the normal and enters the air at an angle of refraction of 38.9 degrees. The index of refraction of the air is 1.00. What is the frequency for the ray of light? So we have three different equations here we're going to use. Let's go ahead and start translating this word problem into physics or math-based ideas that we know. So let's go ahead and start writing down what we know. Well, we know the wavelength is 455 nanometers, and that means times 10 to the negative 9 meters. Next, I am actually going to take the time to write this out, and a lot of students won't take the time to write this out because they're like, hey, that's beneath me. I don't need to write everything out. I'm too smart for that. And I'm telling you right now, if you take the time to do stuff like this, it'll help a lot. This also helps in momentum. So please take the time to write down like 1 is quartz, 2 is air. So you don't write the value for quartz where air should be and vice versa. Alright, then we know what the angle of incidence is, the angle of refraction. We know the index of refraction for air. We're looking for a frequency. We also don't know the index of refraction for the quartz. And we do know what the speed of light is in air or a vacuum. And that's 3 times 10 to the 8th. Now I can go ahead and take this, move it off to the side, and I've got more space. Get rid of this for now. We can talk through the rest of the problem. Alright, so the very first thing we're going to do is write out Snell's law. In this case, we don't know our n1 value. We do know our theta 1, our n2, and our theta 2. So we're going to isolate for n1. And after we've done that, we've basically isolated for our unknown. So now we're ready to plug this value in, and we end up with a value of 1.46. Notice there are no units for this, and we did just talk about why that is. It's because it's a ratio of the speed of light in air or a vacuum divided by the speed of light in the material that we're looking at. So those two units will cancel out. Meters per seconds over meters per seconds will cancel out. Alright, and now we're going to record over here one more bit of information we know. We now know what the index of refraction is for the quartz. Secondly, the next thing we're going to do is say, well, we now know what the index of refraction is for quartz is. We do know what the C value is. We don't know what the speed of light in the quartz is. So we could say, well, let's go ahead, because this is our unknown, we want to get it in the numerator. Sometimes students don't know what the first step is going to be for a problem like this, where their unknown is in the denominator. And the answer is you multiply both sides by that value, and that's because these will cancel out on the right side over here, and you'll be left with your unknown in the numerator over here. So let's go ahead and continue. These cancel, and I want to isolate for my V value. Now at the very end, now I'm ready to plug in my numbers. I go ahead and do so. And now we know how fast the wave is inside the quartz. That's how fast light travels inside this piece of quartz right here, down here. So next I'm going to go ahead and record my values over here and just continue, because the question is what is the frequency? So we solved for N1. We came down over here, we now solve for V. I'm going to take that V, plug it in here, and we want to get our frequency, right? Alright, so let's go ahead, we write that equation out, we isolate, and we're ready to plug in. So we plug in our values here, and we end up with an answer of 4.51 times 10 to the 14 hertz, or you could say per second, which is effectively the same thing, because a frequency is talking about the number of cycles per second, but the cycles are not there algebraically. They're just more there as a label. So you could say algebraically we're left with like per seconds, which is what hertz are, like cycles per second. And that's how you would do a more complex Snell's law problem. Notice we used 3 different equations and we drew on something that we hadn't talked about in a while, but is really foundational for these kinds of problems. And this is just Snell's law on the side of a building. I wanted to point out because I thought it was cool. I do want to say I hope this has been helpful. And we'll talk about other ideas for this unit and hopefully all of the major ideas in physics I'm going to be able to get to. So if you have any comments down below, please let me know, and I hope you all have a great day. Take care.